Right, so the next thing we're going to talk about is how beta and gamma can be approximated in different, what I call regimes in the course. And so basically, there are three regimes that I talked about in the course. There's what I call the non-relativistic regime. And there's the mildly relativistic regime. And that's the highly relativistic regime. Right? So the non-relativistic regime is characterized by the velocity of the particle in question being less than 0.3 the speed of light. In other words, beta is less than 0.3. Okay? Under those circumstances, non-relativistic behavior is a very good approximation. So for example, for particles in the non-relativistic case, the kinetic energy is, to a good approximation, half mv squared. That means that the gamma factor, which embodies all of the modifications to classical behavior that you see in non-relativistic courses that you've done before, when beta is less than 0.3, that gamma factor, gamma has to be approximately equal to 1. Okay? So much for the non-relativistic case. Mildly relativistic case is 0.3 is less than beta is less than, what did I use? 0.99. Under those circumstances, it is not true that beta is so small that the particle is non-relativistic. It's also not true that the beta is so big, in other words so close to 1, that the particle behaves like a photon. It's the intermediate case. So in those circumstances, the relationship between gamma and beta that you have to use is that gamma equals 1 over the square root of 1 minus beta squared. Okay? And so it turns out that this regime corresponds to gamma is greater than 1, but less than about 7. Okay, so to be more precise, gamma is greater than 1.05. So 0.3 beta corresponds to gamma of 1.05, so there's a 5% modification to non-relativistic behavior at the very low end of this range of beta. When beta gets up to 0.99, gamma has reached 7. So in that range, I think it's useful to calculate beta from gamma using this formula, or vice versa. For highly relativistic particles, gamma, and I'll do things in terms of gamma for reasons that will become obvious in a minute, is greater than 7. Okay? When gamma is greater than 7, beta, as near as makes no difference, is approximately 1. Okay? And so if you have a formula containing betas and gammas, and you know that gamma is bigger than 7, then you can set all the betas equal to 1 in the formula. And it greatly simplifies the formula. So that's really a useful thing to know. Okay? Now sometimes in the highly relativistic regime, what sorts of things happen? When a particle is highly relativistic, you can consider the energy momentum mass relation, which we talked about a minute ago. E squared equals p squared c squared plus m naught squared c to the fourth. But in this case, the energy is dominated by the momentum, and the mass isn't as important. And it turns out in the highly relativistic regime, you can often ignore this term and write that E is approximately pc. So for example, if I tell you that you have an electron, now you'll remember, it's on the formula sheet, that electrons have a rest mass of 0.51 MeV over c squared, alright? And I tell you that the electron has a total energy of 45 GeV. Okay? Gamma equals the total energy over the rest mass times c squared, which is 45 times 10 to the 3 MeV, because a GeV is 10 to the 3 MeV, over 0.51 MeV, which is something like 90,000. Now if gamma's 90,000, that means that this electron behaves like this. E equals Cp plus a negligible contribution from the rest mass term. So if you have a highly relativistic particle, you can relate its energy to its momentum just by multiplying by C. That only works if gamma's bigger than 7, but you see in this case here gamma's 90,000. Okay, so that's a useful trick for doing calculations. Now there's a graph that I also drew to show you the relationship between beta and gamma. And you can look it up in the lecture notes from lecture 1. So on the vertical axis we've got gamma. Now gamma is always greater than 1, so if we put an origin on this plot, we can bracket gamma below as being always bigger than 1. Right? And on the horizontal axis we've got beta, and beta is always less than 1, because the particle is always moving, well, less than or equal to 1, because the particle never goes faster than the speed of light in special relativity. So we can bracket beta as being between 0 and 1, and gamma as being, well, I guess strictly speaking, beta can be between -1 and 1, because the particle can be moving in a negative direction as well as the positive, but let's not worry because it's symmetric. Okay? And gamma has to be between 1 and infinity. So we can make the plot of the exact relationship between beta and gamma, and it looks something like this. So here is 0.3 for beta. Here, and I'll exaggerate a little bit, I'm making 0.99 a little bit further away from 1 than it should be on a linear scale, but we'll put it there. And what happens is gamma stays approximately 1 for beta up to 0.3, and then it starts to rise, and then it rises up to a point where it's about 7 at beta of 0.99, and then it keeps going up and it tends to infinity for larger beta than 0.99. And so the non-relativistic regime is everything down here for betas less than 0.3 and gamma's approximately 1, or gamma's less than 1.05, or approximately 1, because I don't care about 5% errors, I'm an experimentalist. Okay? And then the intermediate regime, which this guy called mildly relativistic, has beta between 0.3 and 0.99, and gamma between 1.05 and 7, and that's everything between beta's 0.3 and gamma's 0.99. And then this highly relativistic regime I'll shade. It looks like a small region on this plot, but there's lots of highly relativistic particles because electrons typically travel very fast, because there are, of course, light is always highly relativistic, and because we have particle accelerators that can accelerate even quite heavy things like protons and even gold nuclei up to relativistic velocities. And so a highly relativistic regime has beta is approximately 1 and gamma is greater than 7. And so this is a simplification, because you can make approximations in the two end cases, in the non-relativistic regime and in the highly relativistic regime, to simplify the relationship between beta and gamma. And the only time you have to use the formula gamma equals 1 over the square root of 1 minus beta squared is in the intermediate mildly relativistic regime. The rest of the time you can either set beta equals 1 or you can set gamma equals 1. And that's helpful in making your calculations work out.